In this video, we will discuss measures of variation. When rounding the value of a measure of variation, carry one more decimal place than is present in the original set of data. Consider the diagram below, which illustrates waiting times in seconds of customers in a bank under two different conditions. First, all customers enter a single line that feeds different teller stations. And second, all customers choose to join the line at one of several teller stations. An important observation we can make here is that the waiting times with the single line have less variation than the waiting times with multiple lines. Both sets of waiting times have the same mean of 100 seconds, and they have the same median of 100 seconds, and they have the same mode of 100 seconds. Those measures of center do not see the difference in variation. The single line, multiple line illustration is wonderful because banks actually did change from multiple lines to a single line, not because it made them more efficient or because customer waiting times were reduced, but because customers are happier with waiting times with less variation. The change did not affect the measures of center, but banks instituted the change to reduce variation. An important goal of business and industry is this: improve quality by reducing variation. The range of a set of data values is the difference between the maximum data value and the minimum data value. Range is equal to maximum data value minus minimum data value. Important properties of the range. The range uses only the maximum and minimum data values, so it is very sensitive to extreme values. The range is not resistant. Because the range uses only the maximum and minimum values, it does not take every value into account and therefore does not truly reflect the variation among all of the data values. Find the range of these Verizon data speeds in megabytes per second. 38.5, 55.6, 22.4, 14.1, 23.1. The range is found by subtracting the lowest value from the largest value. So we get range equals maximum value minus minimum value equals 55.6 minus 14.1 equals 41.50 megabytes per second. The range of 41.50 megabytes per second is shown with one more decimal place than is present in the original data values. The standard deviation of a set of sample values, denoted by S, is a measure of how much data values deviate away from the mean. It is calculated by using one of two formulas which are algebraically the same. The standard deviation found from sample data is a statistic denoted by S, but the standard deviation found from population data is a parameter denoted by sigma. The formula for sigma is slightly different with division by the population size n instead of division by n-1. Here are our formulas for sample standard deviation. You can either use S equals the square root of the sum of x minus x bar squared. The parenthesis should be inside the square, not outside, all over n-1, or S equals the square root of n times the sum of x squared minus the sum of x quantity squared, all over n times n-1. The second formula is a shortcut used by calculators and software, but either equation will give the same answer. Important properties of standard deviation. The standard deviation is a measure of how much data values deviate away from the mean. The value of the standard deviation, S, is never negative. It is 0 only when all of the data values are exactly the same. Larger values of S indicate greater amounts of variation. The standard deviation S can increase dramatically with one or more outliers. The units of the standard deviation S, such as minutes, feet, pounds, are the same as the units of the original data values. And the sample standard deviation S is a biased estimator of the population standard deviation sigma, which means that values of the standard sample deviation S do not center around the value of sigma. Use the first formula given to find the standard deviation of these Verizon data speed times in megabits per second. 38.5, 55.6, 22.4, 14.1, 23.1. We have previously calculated the mean of this data set to be x bar equals 30.74 megabits per second. There are 5 data values, so n equals 5 and n minus 1 equals 4. We calculate x minus x bar for each data value and square it, and here are those squares. We take the sum of the squares, which is 1083.0520, and divide the sum by n minus 1 equals 4, which is 270.7630. Take the square root of the quotient, and this is the standard deviation. That is, the square root of 270.7630 is 16.45 megabits per second. This is, of course, rounded to the second decimal place. Use the second formula to calculate the standard deviation of the same Verizon data speeds. We square the data values, add the squares, and multiply by n. That gives us 29,038.95. We take the sum of the data values and square that. That gives us 23,623.69. We take the difference, which is 5,415.26. We divide the difference by n times n minus 1, which is 20. That's 270.763. And we take the square root of the quotient, which is, again, 16.45 megabits per second. We see here that we get exactly the same value no matter which of the formulas we use. Range rule of thumb. The range rule of thumb is a crude but simple tool for understanding and interpreting standard deviation. It is based on the principle that for many data sets, the vast majority, about 95% of sample values, lie within 2 standard deviations of the mean. The range rule of thumb for identifying significant values. Significantly low values are mu minus 2 sigma or lower. Significantly high values are mu plus 2 sigma or higher, and values not significant are between mu minus 2 sigma and mu plus 2 sigma. The range rule of thumb for estimating a value of the standard deviation S to roughly estimate the standard deviation from a collection of known sample data use S is approximately the range divided by 4. For example, the Verizon data speed set has a mean of 17.60 megabits per second and a standard deviation of 16.02 megabits per second. Use the range rule of thumb to find the limits separating values that are significantly low or significantly high, then determine whether the data speed of 77.8 megabits per second is significantly high. With a mean of 17.60 and a standard deviation of 16.02, we use the range rule of thumb to find limits separating values that are significantly low or significantly high. Significantly low values are 17.60 minus 2 times 16.02, which is negative 14.44 megabits per second or lower. Significantly high values are 17.60 plus 2 times 16.02, or 49.64 megabits or higher. And values not significant are between negative 14.44 megabits per second and 49.64 megabits per second. Based on these results, we expect the typical Verizon data speeds are between negative 14.44 and 49.64 megabits per second, because the given value of 77.8 megabits per second falls above 49.64 megabits per second, we can consider it to be significantly high. A slightly different formula is used to calculate the standard deviation sigma of a population. Instead of dividing by n minus 1, we divide by the population size n. The population standard deviation sigma is equal to the square root of the sum of x minus mu squared all over n. Because we usually deal with sample data, we will usually use the formulas for sample standard deviation as previously seen. The variance of a set of values is a measure of the variation equal to the square of the standard deviation. The sample variance S squared is equal to the square of the standard deviation S. The population variance sigma squared is the square of the population standard deviation sigma. Important properties of variance: the units of the variance are the squares of the units of the original data values. The value of the variance can increase dramatically with the inclusion of outliers, so the variance is not resistant. The value of the variance is never negative It is 0 only when all of the values are the same number. And the sample variance S squared is an unbiased estimator of the population variance sigma squared. A concept helpful to interpreting the value of a standard deviation is the empirical rule. This rule states that for data sets having a distribution that is approximately bell-shaped, about 68% of all values fall within one standard deviation of the mean, about 95% of all values fall within two standard deviations of the mean, and about 99.7% of all values fall within three standard deviations of the mean. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percentage of IQ scores are between 70 and 130? 70 and 130 are each exactly two standard deviations away from the mean of 100. Per the empirical rule, about 95% of all values are within two standard deviations of the mean, so about 95% of all IQ scores are between 70 and 130. The proportion of any set of data lying within k standard deviations of the mean is always at least 1 minus 1 over k squared, where k is any positive number greater than 1. For k equals 2 and k equals 3, we get the following statements. At least 3/4 or 75% of all values lie within two standard deviations of the mean, and at least 8/9 or 89% of all values lie within three standard deviations of the mean. IQ scores have a mean of 100 and a standard deviation of 15. What can we conclude from Chebyshev's theorem? Applying Chebyshev's theorem with a mean of 100 and a standard deviation of 15, we can reach the following conclusions. At least 75% of IQ scores are within two standard deviations of the mean, so between 70 and 130. At least 89% of IQ scores are within three standard deviations of the mean, so between 55 and 145. It's best to compare two sample standard deviations only when the sample means are approximately the same. When comparing variation in samples or populations with very different means, it's better to use the coefficient of variation. The coefficient of variation should also be used to compare variation from two samples or populations with different scales or units, such as when comparing variation of heights and weights of men. Coefficient of variation, or CV, for a set of non-negative sample or population data expressed as a percent describes the standard deviation relative to the mean and is given by the following. For a sample, CV equals S divided by X times 100. For a population, CV equals sigma divided by mu times 100. The round-off rule for the coefficient of variation, round the coefficient of variation to one decimal place. For the Verizon data speeds in the textbook, the mean X bar equals 17.60 megabits per second, and the standard deviation S equals 16.02 megabits per second. For earthquake magnitudes in the textbook, the mean X bar equals 2.572, and the standard deviation S equals 0.651. Since the data sets have different scales and units, we must first calculate the coefficient of variation for both sets. For Verizon data speeds, we find the coefficient of variation is 91.0%, and for earthquake magnitudes, we find the coefficient of variation is 25.3%. We can see that the Verizon data speeds can vary considerably more than the earthquake magnitudes. The sample standard deviation S is a biased estimator of the population standard deviation sigma, which means that the value of the sample standard deviation S values of the sample standard deviation S do not tend to center around the value of the population standard deviation. While individual values of S could equal or exceed sigma, values of S generally tend to underestimate the value of sigma. Consider an IQ test designed so that the population standard deviation is 15. If you repeat the process of randomly selecting 100 subjects, giving them IQ tests, and calculating the sample standard deviation in each case, the sample standard deviations that you get will tend to be less than 15. The sample variance S squared is an unbiased estimator of the population variance sigma squared, which means that the values of S squared tend to center around the value of sigma squared instead of systematically tending to overestimate or underestimate sigma squared. Consider an IQ test designed so the population variance is 225. If you repeat the process of randomly selecting 100 subjects, giving them IQ tests, and calculating the sample variance S squared, in each case, the sample variances that you obtain will tend to center around 225.